All right, here's the backside of this equilibrium. Question number 2, maybe a little bit tougher. The first 2 questions are pretty easy. Telling you have 89.7 grams of this placed in a 15-liter container at 182 degrees Celsius. What is the concentration of just that? So let's turn this into moles. Divide by number of liters, get your molarity. So 89.7 grams. It tells you it's 299 grams per mole. Equals 0.3 moles divided by 15 liters equals that molarity of SbCl5. What's the pressure? So we can just go PV nRT. It's before any reaction occurs, any decomposition. So it's just this in there. So plug your moles in there. Make sure you change 182 into Kelvin. I'm not going to do that, but you get a pressure of 0.747 atmospheres. That is before any decomposition occurs. That's just with that in there. All right. If the SbCl5 is 29.2% decomposed when equilibrium is established, figure out the value for Kc. We're going to do, instead of Kc, let's do Kp. Let's do K in terms of pressure. I guess we could use molarity. We could plug in molarity, figure out what 29.2% is. We could do it with pressure. Let's do it in terms of pressure. So we're going to do Kp instead of Kc. So if we put in a little ice table, initial change, equilibrium, this is 0.747 atmospheres initially. There's none of those. It is 29.2% decomposed. So we're going to go, let's figure out 0.747 times 0.292, which 29.2% equals 0.218 atmospheres. That is the percent that is decomposed, not the percent remaining. So that is our change. This is going down by 0.218 atmospheres and an equilibrium of 0.529 atmospheres. If this one went down by 0.218, this would have gone up by 0.218, and this would have gone up by 0.218. Being a little close to the bottom, sorry. So both of these are 0.218 atmospheres at equilibrium. If we want to get the Kp, be 0.218, it's products squared because there's 2 of them, over 0.529, Kp equals 0.0898. Again, we could have done this in terms of concentration with our molarities. You could do the little Kp equals Kc, RT, change in moles, and change into that as well. We just need to know Kp. So about 0.09 is our Kp. All right. Last question. This one's pretty tough. It's a little bit different from what we've been doing. In order to produce some CbCl5, a 1 mole sample of SbCl3 is placed in an empty 2-liter container. So you have 1 mole in a 2-liter container. So that means your molarity of SbCl3 is actually going to be 0.5 molar. So our concentration of SbCl3 is 0.5 molar. At this temperature, Kc equals 0.117, so Kc 0.117. How many moles of Cl2 must be added to this container to reduce the number of moles of SbCl3 to 0.7 moles at equilibrium? All right. So let's set up a little ice table. Initial, change, equilibrium. We know that initially the SbCl3 is 0.5 molar. And then we want this to be 0.7 moles at equilibrium. So SbCl3 concentration equilibrium, we want 0.7 moles in a 2-liter container, 0.35 molar, so 0.35. So that's going down by 0.15 molar, we know right there. We're trying to figure out what does this need to be? How many moles of that must have been in there? Well, if this went down by 0.15, this must have gone down by 0.15. At equilibrium, this is x minus 0.15. They must have just started with this. This must be 0 molar. I'd have to tell you that, I think, for you to know that. That means this would have gone up by 0.15. It's 0.15 at equilibrium. Now we can plug it into our K. We know K is 0.117. So do 0.35 times x minus 0.15 all over our reactance 0.15. Cross multiply, distribute that through, go from there. I'm not going to do all the algebra. Well, I can do the algebra. When I cross multiply, I get 0.01755 equals 0.35x minus 0.0525. Combine like terms, move this to the other side, you get 0.07005 equals 0.35x. X is 0.2. That is molarity. That's moles per liter. We're in a 2-liter container. So 0.4 moles of Cl2 would have been in there initially. It's a really tough problem. Working backwards is a little bit different from what we normally have to do.